All right, let's revisit the Taylor theorem, but before doing that, so these are sort of like approximations of the values of arc cosine and arctan. In fact, in particular, arc cosine 0.15 is approximated by its Taylor polynomial, and same as arctan 0.4. So let's look at the Taylor's theorem so carefully. Let's say like we have a differentiable function through the order like n+1 in an interval I containing the point C. So this is the expansion of f at point C. Then for each x in I, there exists a z between x and c. Okay, there is the number z between x and c, such that f of x is exactly equal to the Taylor polynomial of order n, which is Pn of x in the notation, in our notation, and all of the leftover terms. So normally Taylor expansion is something that we have infinite many terms, but what we do is like we cut off here and then disregard the rest when we make an approximation. So just imagine like Rn of x keeps all the tail terms, okay? So this theorem says that the tail is in fact exactly equal to this for some z in between x and c, okay? We don't know exactly what z is, but what we're going to do is that since Rn is the term that sort of like hides the error in the approximation, so we're going to try to find an upper bound for Rn of x. But before doing that, let's just stare at these approximated values of arc cosine 0.15 and arctan 0.4. So apparently, so it's being used like the P1, right? P1 is being used here because you have only two terms here, pi over 2 and 0.15. So this is like we have the Taylor polynomial of order 1 and evaluated at 0.15. Okay. So then for this part A, I'm going to be interested in finding R1, and I'll try to find an upper bound for it. For part B, though, since we have 0.4 and then all the way to 0.4 cubed divided by 3, apparently we are keeping we're keeping the Taylor polynomial. We're working on Taylor polynomial order 3, so that means it's P3. And P3 is in fact evaluated at 0.4. So for this case, then I'm going to be interested in R3. Okay. So let's go ahead and then write down the Taylor polynomial of f. For the first case, I need to write that down for n equals 1, for n equals 1 and c equals 0. Okay. So essentially, it's the Maclaurin polynomial. And then once I have the Maclaurin or Taylor polynomial, then I'm going to plug in 0.15 in it. Okay. So for that reason, I need f prime. And f double prime for R1. Okay. So for P1, I don't need f double prime, but for R1, I need. Okay. And use the differentiation formula card, and it used that this is minus 1 over 1 minus x squared. Okay. And for finding f double prime, you need the quotient rule. Okay. Let's write that down. And in fact, if you want to avoid the quotient rule, do this. So write this term as like 1 minus x squared to the power of -1/2. Okay, now we can use the power rule for differentiation. So this is 1/2 -2x, 1 minus x squared, -3/2. If you simplify that, -x divided by 1 minus x squared, 3/2. Okay. All right, all I need is f evaluated at 0. So arc cosine 0, that should be pi over 2. You can use your TI-84 to find arc cosine 0, and f prime at 0 is in fact -1. Okay, 1 minus 0 squared in the bottom here, right? In the bottom here, so it's -1. So let's write P1 of x here. P1 of x is f of 0 plus f prime of 0, which is minus 1, x minus 0.15. X minus 0, sorry. So that's just x, right? Because we're having c equals 0, so pi over 2 minus x. Okay. So now look, P1 at 0.15 is something really easy to calculate. Pi over 2 minus 0.15. There we go. That's in fact what's given in the question statement here. Right, pi over 2 minus 0.15. Okay, so now I'm going to write the description of Rn in the next slide. So I need this. I need R1. R1 means I need the second derivative evaluated at z and all other terms. So let me just head the new slide. All right, so I just wrote the description of R2 based on the Taylor's theorem. And the z, the number z is in between 0 and 0.15. I'm going to evaluate R2 0.15. There we go, f double prime z over 2 factorial 0.15 squared. Okay. So that's why I need f double prime. So what is f double prime at z? So we did the calculation for f double prime here. So it's minus x, 1 minus x squared to the power of 3/2. So minus z, 1 minus z squared to the power of 3/2. All right, at this moment, by the way, I took the absolute value of R2 at 0.15 because I need to find an upper bound. I'm going to try to majorize this quantity. I'm going to pick, I don't know exactly what z is, except that I know it's in between 0 and 0.15. But I'm going to try to maximize this quantity by taking the absolute value, so I'll see the maximum error, okay? So at this moment, think about like what kind of like z makes this expression bigger, okay? But first of all, since this is an absolute value, I'm gonna get rid of all the minuses here, right? So I'm gonna get all the minus here. So I don't need that minus because z is a positive number anyway. When you take the absolute value, that's gonna be positive. So the whole expression is gonna be positive, okay? So to make this maximum, well, I should probably majorize this as keeping z to be the maximum in the top, right? And in the bottom, I should take z to be 0.15 because if I take z to be 0 or anything less than 0.15, then this number is going to be bigger. I want to keep the denominator smaller, okay? The way to make it smaller is just to go with the maximum z, and z is in between 0 and 0.15, so I should go with like 0.15 here, okay? So that again, the denominator is going to be smaller, and this is 0.15, and then this is 2 factorial. So this quantity, essentially, this quantity, okay, is smaller, I mean less than or equal to this quantity, which is something that you can calculate right away. Okay, use your calculator TI-84 and then convince yourself that R2, let me just write it right here, R2 0.15 is less than or equal to, in fact, R1, I'm sorry. This is R1. Okay, this is R1, I'm sorry. Okay. All right, let's continue. So this number is, if you calculate that, that's going to be 0.00175. Okay, so if you retain only 2 terms in the sum, that means you're looking at P1 to approximate the value of arc cosine at 0.15. The maximum error that you can make is this much. So it's almost at the level of 10 to the minus 3. Okay.